Hello friends, welcome to Entry A. In this video, we discuss the previous year question of process management. So in this particular video, we start the previous year question of process management that include the question of the state diagram, process state diagram, and the scheduling technique, CPU scheduling technique. So we'll discuss about that. Now the first question is, in the following process state transition diagram for a uniprocessor system, assume that there are always some processes in the ready state. Now consider the following statement. So that is the state diagram. The first state is the start state that mentioned here, that is the start. The second one is ready, and that is the running state. The next is terminated, that is terminated state, and the last one, that is blocked state. And it make a transition like that is from running to ready to running, it make a transition B. From start to ready, it make a transition A. From running to ready, we can say that the transition is C. Got it? That is a C transition, and that is F transition, that is D transition. By arrow it mentioned that all transition. Now the question is that first statement, if process make a transition D means if it move from running to terminate, it would result in another process make a transition A immediately. So is it correct? Means if any process that is terminated, from the system, at the same time the new process is arrive in the transition A, means arrive in the ready state. So is it correct? So definitely it is not correct always, because it may possible that some process exists in the ready queue and that are only the processes that we need to execute. So definitely one by one process all goes to the running and will terminate it. So definitely it is not necessary that when a process is terminate, the new process arrive in the ready state. So it is not true. So first is not correct. So according to that, you can remove the option that contain 1. So A and B will remove. Now the second, a process P2 in a blocked state can make a transition E. What is the transition E? From blocked state it can make a transition E, means to the ready state. So while the another process P1 is in the running state, means a process P2 that is in the block state can be make a transition E, means a process can move from block to ready if any other process P1 that is in the running state. So yes, it is possible, because if one process P2 it is in the blocked state, got it, and definitely in the block state it perform its IO operation, and after some time if it is ready for the execution to, so definitely we move that particular process to the ready state, and definitely at that time some process is executed in the running state, because when the process go to the block we put that particular process in the new process in the CPU. So that is correct, second is correct, not any problem. And definitely you can say that in this C and D option second is exists, so definitely second is correct. Now third, the operating system use preemptive scheduling, then the last, the operating system use non-preemptive scheduling. So definitely both of out of this two, definitely one is correct. So the operating system use preemptive. So according to preemptive, the nature of preemptive means we can preempt the resource from the CPU and again put it in the ready queue, means running to ready is possible. So in this diagram there is a transition C that move from running state to ready state, means it is a time sharing operating system, and definitely it use a preemptive nature. So operating system use preemptive, so definitely third is correct, but fourth one is not correct. So C is the right answer, second and third is the correct statement. Got it? So second and third is correct. Now the next, the maximum number of process that can be in the ready state for a computer system with a CPU n. So we can say that if there are n CPUs in this system, then maximum process that can be in the ready state for that particular system. So definitely it is independent of n. It is a gate question and a very easy question. So don't be confused. If there are n CPUs, n processor connected to a single system, we can say that is multi-processor system. So the number of process in ready queue does not depends on the number of CPUs. Definitely it depends on the requirement or the size of memory, or there are various parameters, but it definitely independent of n. So we can say that it is not dependent on the number of CPUs. Now the next question, the process state diagram that is also mentioned in this particular question. Now the diagram is representative of batch operating system with preemptive scheduler, operating system with non-preemptive scheduler, and uni-programmed operating system. So here what is that? A new state from new to ready, and from ready to what we can say that running, and running to terminate, and between ready and running the process can move in multiple times, and from running it goes to the block and it go to the ready. Means exactly the normal state diagram that we discussed in the concept is written here. So definitely is it the batch operating system? So we know that in case of when the process move from running to ready and ready to running, so that is the context switching that happen only when we use the time sharing operating system, or we can say that the multitasking operating system. So that is the nature of preemptive. So here what we can say that the operating system is batch, not. Operating system with preemptive scheduler, correct. Non-preemptive, not. Uni-programmed operating system, not. So B is the correct, that is preemptive in nature. So definitely the first and this question is related question, both are gate question. So you should understand such type of logic. So B is the right answer. Now the next question, which is the correct definition of valid process transition in an operating system? So which of the following is a valid process transition, that correct definition of valid process transition? So what is the meaning of that? First, wake up means ready to running, dispatch ready to running, block ready to running, and time run out ready to running. So we know that when the process move from ready to running state, what is the task of this? So any process that is moved from ready to running means we allocate the CPU to that process, and this task is done by the short term scheduler, means the process is selected by short term scheduler and dispatcher is responsible to dispatch that process to the CPU. So definitely we can say that dispatch ready to running is the correct, because during the wake up we can say that when we wake up the process for execution, then definitely it arrive in the new state from new to ready. And block means from running to, we can say that block means from running to block, got it? So that is the meaning of this. And time run out is that running to ready. Time run out means if we allocate a time slice to a process, then definitely it move from running to ready. So only dispatch is correct for the ready to running, got it? So B is the right answer. Now the next, which of the following process scheduling algorithm may lead to starvation? So which of the following is may lead to starvation? The first FIFO. So definitely in the FIFO it is not correct, because the first in first out, so definitely there is not any possibility of starvation, because any process that arrive first definitely execute first. So infinite wait is not possible. Round robin, so definitely in the round robin we can say that, just see here, round robin, shortest job next, and none of the above. So which of the following process scheduling algorithm may lead to starvation? So here we can say that in the preemptive technique, round robin, definitely it give the chance to each and every process. So definitely there is not a possibility of the starvation. Shortest job next, so SJF is the best example for, we can say that, the starvation, because when the less, we can say that the less time burst time process arrive again and again, and large burst process is waiting in the ready queue for a long time, then it may lead to starvation. So SJF is correct. Definitely C is right answer. So in this case, in case of starvation, there are various questions that ask in the GATE examination, but we need to carefully solve such type of question. It is very easy question, and this we can say that out of this three technique, SJF is definitely generate starvation. That's why we select that. Got it? It may possible, other than SJF is also possible to the starvation is possible, but it depends on which type of question is asked. If time quantum of round robin algorithm is very large, if we increase the time quantum very large, then it is equivalent to which one of the following? First in first out. So definitely, as we already discussed in the concept, round robin, when we increase the time slice very rise, then round robin is exactly equivalent to the first come first serve, because the process arrive in the ready running state, means if the process allocate to CPU, it will completely execute during that particular time slice, if the time slice is very large or equivalent to the burst time. So it is nearly equivalent to the first come first serve. So A is the right answer. That is very simple theoretical question, that 1 marks question that asked in the GATE examination. Now the next question, which of the following statement are true? The first, shortest remaining time first scheduling may cause starvation. Shortest remaining time first may cause starvation. Preemptive scheduling may cause starvation. round robin is better than FCFS in terms of response time. So just understand the logic here. The first question is that first statement, shortest remaining time first scheduling may cause starvation. So yes, definitely, as we already discussed in the concept, in SRTF starvation may occur, because if the new arrived process burst is less as compared to the old process that is exists in the ready queue or old running process, so definitely it may create a starvation, because it is like a SJF. We already understand the point in the theory and concept that when the arrival type of all the process is equal, then SRTF is exactly equivalent to SJF, and if SJF create a starvation, then definitely SRTF may possible to create a starvation. Preemptive scheduling may cause starvation. So just understand the point. As SRTF, if we says that this SRTF, shortest remaining time first scheduling algorithm, causes starvation, so definitely SRTF is a part of preemptive nature, is a type of preemptive scheduling. So if SRTF causes starvation, then definitely preemptive technique may cause a starvation. That is also correct. So first, second is correct. Round robin is better than FCFS in terms of response time. So definitely, because when you use the valid time slice, then we can give the chance to each and every process to allocate the CPU. So definitely each process get response fast in case of round robin. So both or we can say the all 1, 2 and 3 are correct statement. So D is the right answer. Got it? Now the next question. A scheduling algorithm assign priority proportional to the waiting time of process. Got it? What is the question? Is that a scheduling algorithm assign priority proportional, that priority is proportional, directly proportional to the waiting time of process, means if process is wait for large time, the priority will high. Got it? So that is the logic of this. Now here what we can say, that every process start with priority 0, that is the lowest priority. Got it? Now the scheduler re-evaluate the process priority every t times unit and divide the next process to schedule. Decide the next process to schedule. Which one of the following is true if the process have no IO operation and all arrive at time 0? Means all the process is arrive at time 0 and there is not any IO operation for the process, then what is the correct statement according to this? So here we can say that first, this algorithm is equivalent to first come first serve. So is it correct? Because here we just says that waiting time of process, every process start with priority 0 and it directly proportional to the waiting time. Priority is directly proportional to the waiting time. The algorithm is equivalent to the round robin algorithm. So which of the following is true if there is not any IO operation and all arrive at time 0? The algorithm is equivalent to the shortest job first. This algorithm is equivalent to the shortest remaining time first algorithm. So here just understand, there is not any mention that in this case it says that we assign priority proportional to the waiting time and every process start with priority 0. Now the scheduler re-evaluate the process priority every t time units and decide the next process to schedule. So definitely it use some preemption logic, and we can say that initially all process is 0. So we allocate any process to the CPU. Got it? We just allocate the process to the CPU, and after then we can say that after some unit of time it re-evaluate the process and arrange the priority, and definitely according to their waiting, means if that process P1 will allocate for a 5 unit of time and the remaining process according to their arrival, we can say that it may change their burst are different. Got it? So definitely we just says that we re-evaluate the process. So definitely the remaining process will generate the that is the priority, different priority. So each process get its a response definitely in a particular fixed amount of time. So we can say that this algorithm is equivalent to round robin because we re-evaluate the priority. So B option is correct. Got it? So we can consider the B is the right answer in this case. Now the next question is which of the following scheduling algorithm, the next question is which of the following scheduling algorithm is non-preemptive? So the first one is round robin, first come, that is non-preemptive in nature. So definitely round robin, first in first out, multi-level queue scheduling, multi-queue scheduling with feedback. So non-preemptive type is definitely that is first come first serve, first in first out. we can say that the FIFO or FCFS, first come first serve, first in first out, so you can use that in non-preemptive nature. Got it? Now the next question, consider a set of n tasks with known runtime, that R1, R2 up to Rn, to be run on a uniprocessor machine. Which of the following processor scheduling algorithm will result in the maximum throughput? If there are n tasks with runtime, that means that is the burst time of the process on uniprocessor, which of the following process scheduling will result the maximum throughput? Round robin, shortest job, highest response ratio, next, first come first serve. So definitely we know that for maximum throughput we can consider that if there are various processes, and if we use the round robin, then if the processes are small size processes exist in that particular series, then definitely after a particular time that we get a valid throughput, or we can say that a number of outputs is generated. So definitely we can say that in there are n processes, then if we use round robin, then if we increase the time slice, so it may possible if we increase the time slice, then it look like a we can say that FCFS. But in case of shortest job first, as we know that among all the processes, the SJF gives always best result. So maximum throughput is generated by SJF, that is shortest job first. Got it? So the maximum result that is generated by this is SJF. So B is the right answer. Among all, SJF is considered that is best. Now the next question, which of the following is false about SJF shortest job first scheduling technique? It causes minimum average waiting time. Which of the following is false? The false statement. It can cause starvation, so that is a true statement. It causes a minimum average waiting time, means it generate minimum average waiting time. Is it correct? So we need to find the false. So definitely that average waiting time is definitely when you use the shortest job first, so definitely that average waiting time is reduced. So that is a true statement. It can cause starvation, so it is also true statement. So both are true statement, but we need to find false. So neither S1 and nor S2. So both are true statement. Got it? So D is the right answer. Now in this question, again that is simple theoretical question. Consider an arbitrary set of CPU bound process with an unequal CPU burst length submitted to the same time to the computer. Set of CPU bound process. We know that what is the meaning of CPU, that spend maximum time to the CPU. Which one of the following process scheduling algorithm would minimize the average waiting time in the ready queue? Would minimize the average waiting time in ready queue. Shortest remaining time first, round robin with quantum less than the shortest CPU burst. Round robin with time quantum is less than the shortest CPU burst. What is the meaning of that? If there are n process, out of that n process, the minimum burst process, whatever the burst time of that minimum process, we use the time quantum, or we can say the time slice is less than that minimum burst. Got it? Means we use minimum time slice. Uniform random means you uniformly random execute, and highest priority first with the priority proportional to CPU burst length. Means if the burst length is, we can say that the higher, then highest priority first with priority proportional to CPU burst length. So if the burst is highest, then priority is also highest. That is the meaning of this. So definitely if the burst is highest, if we execute first those process whose burst time is more, then definitely it is not a give the we can say that the minimum average waiting time. Definitely it is look like a first come first serve, or we can say that it increase the waiting time. If large process execute first, definitely that remaining process will wait for long time. So it is definitely not correct. Uniform random, so definitely we not use uniform random. Now out of this two, shortest remaining time first definitely give the best result other than the round robin. So we use that A is the correct answer for this. Got it? Because all the process is CPU bound. So definitely we can say that shortest remaining time first is the correct way. So A is the right answer. Now the most optimal scheduling algorithm out of this four, most optimal. So FCFS, SJF, round robin. So definitely we use by default SJF because shortest job first give the best result in every cases. So SJF is correct. B is the right answer. That all theoretical questions that ask in the GATE exam are related to the we can say that the technique, the best technique. So we just around that SJF, SRTF are the best techniques. Now, which module gives the control of CPU to the process selected by short-term scheduler? Control of CPU to the process selected by short-term scheduler. So that is dispatcher, that we already discussed in the technique concept. Got it? So dispatcher is allocate the CPU to that process that is selected by short-term scheduler. Now the next question. Consider the process. Consider three processes. ID is 0, 1, 2. With computer burst time burst is 2, 4 and 8 time units. All the process arrive at time 0. Consider the longest remaining time first scheduling algorithm. Just see here. In this there is different type of scheduling algorithm that is asked, that longest remaining time first. In LRTF, tie broken given by priority to the process with the lowest priority ID. Then the number of turnaround time is, the average turnaround time is. What is the average turnaround? What is the question asked actually? There are three processes that ID is 0, 1, 2. So we can say that the process, that is process ID first 0, 1 and 2. That is the name of process, ID of process. With computer time burst, compute burst means the burst time, that burst time of process is 2, 4 and 8. That is the burst time. Got it? And all process arrive at time 0. So the arrival time is 0 for all three processes, means all processes arrive at the same time. Now what is the next data that is given in this question? Consider the longest remaining time first, means first we execute as we already discussed, shortest remaining time first means execute those processes whose remaining time is minimum. But here that is the reverse concept, that called that LRTF, longest remaining time first, means we execute first those processes whose burst time is maximum at that particular time. Whatever the process that is present in ready queue, we execute only those first that time is maximum. And it is we can say that in this technique, that is longest remaining time first scheduling algorithm, and definitely it is a nature of preemptive. So we can preempt the process when the new process whose burst is greater is arrived, then we preempt. Now in LRTF, tie is broken by given the priority to the process with lowest process ID. Priority to the process with lower process ID means the process ID is lower is the highest priority. So we can say that here the priority is also given like that. What is the logic of priority? That the priority to the process with lowest process ID. So that is this highest priority and that lowest priority process. Got it? So definitely we can say that that is second highest, and this is the way. Now we execute first initially. Just take all the processes in the system. So first we execute those processes, first we apply the LRTF technique. So execute those processes which is we can say that initially all the process that is in the ready queue. Got it? So that is ready, and we can say that this is running state. So initially all process, we just rename this process like P0, P1 and P2 to understand. Got it? The 0, 1, 2 is the ID, we just says that P0, P1, P2. So initially P0, P1, P2 all are in the ready queue. Now we apply longest remaining time first. So the process that remaining time for that burst time is largest, that execute first. So out of this three, P2 is highest burst. So P2 is exists because all arrive at time 0. Now for how many time we execute this P2? So we can say that the highest priority, second highest priority, and that is the last priority. So first we execute P2 because priority is applied when ties occur. But here there is not any tie because according to burst, P2 is the highest burst. So we execute first P2. Now how much time? For how much time we execute P2? Just understand. We start the execution at time 0, and definitely when P2 execute till 4, at time 4, we can say that P2 execute half its duration. We execute for 4 unit of time, and the remaining burst of P2 is 4. Now at that time, the burst of P1 is also equal. P1 and P2 is equal burst. Now when the burst is equal, we just execute the process whose burst is, we can say that the largest burst process first. But here burst is equal. Now we need to check the priority. Now which one is the highest priority process? So definitely P1 is highest priority than P2. So we just preempt that P2. initially just we allocate first P2 in this CPU, got it? So initially what we can say that in the ready queue P2 is allocated here. Now we execute the next process, that is here we can say that the P1 and preempt P2. P2 is all again written in this. Now P1 is here and P2 in the ready queue, got it? The remaining burst of P2 is 4. P1 is here because the P1 and P2 is equal burst, but at that time what we can say that the priority of P1 is greater, that's why we execute P1. Now definitely it execute after executing 1 unit of time, the P1 remaining burst of P1 is 3. Now what happened? In the ready queue P0 and P2 is exist. The burst time of P0 is 2, definitely that is minimum. Burst time of P1 is 3 and burst time of P2 is 4. P1 is in the running state, P0 and P2 is in the waiting state, or we can say that the ready state. So the out of this 3 process, definitely the maximum burst is of P2. So again we need to preempt, means P1 goes to the ready and P2 is here. So what we can say that P1 is here and P2 is in the ready state. Now after 1 unit of time, what we can say that when P2 execute for 1 unit of time, the remaining burst of P2 is definitely 4 minus 1, that is 3. The remaining burst of P2 is 3 again, because that is remaining 4 and 3. Now the P1 and P2 both are equal. Again the priority of P1 is greater, that's why we again need to execute P1 and P2 is goes to here in the ready queue, got it? P0 is already exists there, so P1 is allocated here. Now for after executing 1 unit of time, when P1 execute for 1 unit of time, so the burst of P1 is now, what is that, 2, got it? From 3 to 2. Now the burst of P1 is 2. What we can say that the burst of P0 is 2 already, the burst of P1 is now 2 after executing 1 unit of time. Now the burst of P1 is again 2 and the burst of P2 is still 3. So at that time this 3 process that we can say that the P1 is in running and P0 and P2 is in the ready. So the maximum burst process is P2. So we need to preempt P1 again and execute P2. So P1 again goes to the ready queue, that P1 is here and P2 is in this. Now P2 again execute for 1 unit of time only, got it? Because after that the burst is equal of all the process. So the burst of P2 is 3 and after executing 1 unit of time, the next burst of P2 is now 2. Now at that time, at time 8, we check the running process P2 whose burst is 2 and the process that is existing in the ready queue, that is P0 and P1, whose burst is also 2. So all process is of equal burst. So now when the ties occur, we need to check a priority. So highest priority process is thus whose ID is less. So P0 is highest priority. So we can say that we need to execute first P0. Now again, is P0 completely execute or it execute only for some amount of time? So definitely after executing 1 unit of time, if you execute 1 unit of time, the remaining burst of P0 is 1 because that is 2. Now after executing 1 unit of time, the remaining burst is 1. Now there are 3 processes, that one is in the execution, that is P0, and P1 and P2 is in the ready queue. The burst of this 2 is greater than this. So first we apply LRTF, whatever the priority of P0, because the burst is P1 and P2 is greater than P0. So we need to execute any one of them, this 2. Now because the burst is equal, we need to check the priority. So that is P2. So the next is P2. Again after 1 unit of time, the remaining burst of P2 is again 1. Now this 3 process, out of this P1 burst is 2, so we need to allocate next P1 again and the burst is remaining 1. Now the burst of this is also 1. After 1 unit, we can say that all the process burst is now 1. Now according to priority we execute, so definitely each process execute for 1 unit of time. So highest priority is P0 and P0 execute finish completely. Now the remaining P1 and P2, so the next highest priority is of P1. So we execute P1 and the last one is P2, that is executed at 14 time. Got it? So that's 0, 4, 6 and that is 14. So if you add all this sum burst time, so 2 plus 4, 6 plus 8, 14. So total sum is this. Now the question is that average turnaround time. We need to calculate the average turnaround. So we know that in this process, the P0 is execute. We need to calculate turnaround of P0. P0 execute in this slot. What is the last time when the P0 is out? At time 12. So the turnaround time of P0 is 12. That is the completion time minus arrival. Arrival is definitely 0. So exactly that is the turnaround time. So 12 minus 0, that is 12. For P1, P1 is complete at 13 time. Arrive is again 0. So turnaround is 13. For P2, that arrive at finish at 14 time. The exit time or completion time is 14. Arrival is again 0. So that is 14. So 12 plus 13 plus 14 divided by 3. So that is 13. Average turnaround time is 13. So the right answer is 13 unit. A is the right answer because the question asks only average turnaround. So that is the logic that used in this question. Got it? So first we need to solve according to largest burst, and when the burst is equal, we need to apply priority. So definitely it is a concept of preemptive SRTF with priority. Preemptive LRTF with priority means when ties occur, we need to apply priority technique. So that is the logic. So that is all about the questions of PYQ in this series. We will continue these questions in the next video. Thank you.